Welcome back, Calculus. Hope you all are well. I've got the checklist ready for you to take a look at, so I'm going to pause the screen. You know what to do from here. All right, so we are in section 1.2a today, Limits Analytically. So we're going to look at how do we find limits now, not just from a graph, but if I give you the function as an equation, okay? So I'm actually going to force a pause on your screen one more time, and I'd like for you to fill out this table with this function here, okay? So if y equals the absolute value of x over x, well, if I plug in -1 into that equation, I get +1 over -1, so that's going to give me an output of -1, okay? So I'm going to force a pause on your screen, go ahead and fill out the table, click continue when you're ready to see the answer. All right, answer is on the screen. If you didn't get what I got, make sure you take out that different colored pen or pencil and just make corrections on top. So if you'll notice that our output for y is -1 anytime your input for x is a negative number, and your output is +1 whenever your input is a positive number. Okay, so let's go ahead and take a look at the graph of this function. So if x is greater than 1, my output for y is +1, so let's say that's 1, 2, 3, etc. And if x is a negative input, then my output is a -1 for y. And notice that at 0 it's undefined, okay? So I get this jump, right? I kind of call this the broken railroad tracks function. Sometimes the actual name of this function is a variation of the signum function. Okay, and this function actually pops up a lot in calculus, especially when we're looking at limits. So what I want to ask you is, like, what if instead I gave you y equals the absolute value of x over x with a +3 on the outside? What way would that shift the graph? Yeah, so it's going to shift the graph up 3, right? Now if I wanted to do an inside transformation, I would need to put a plus or minus whatever number anywhere I see an x. So for example, if I want to shift the graph to the right 5, I would need to have an x minus 5 there as well as there. So this would shift the graph right 5. Okay, go ahead and pause your screen if you don't have everything written down that I do, because we are going to come back to this in just a moment. All right, so we're going to look at how to find limits analytically or algebraically. I'd like for you, I'm going to force a pause on your screen. I'd like for you to copy my screen and go ahead and hit continue when you're ready to continue with me. Okay, so to find limits analytically, we're first going to plug in the value of c, which is the number that x is approaching, into the equation. From there, you're going to have 4 different scenarios or 4 different options, so go ahead and write these with me. Hopefully you remember some of this from pre-calc as well. So option number 1 is you're just going to get some kind of number, and this is, I'm doing that for number, not hashtag, in which case we're going to go, yay, we're done, because that's my answer, right? Scenario number 2 is you get 0 over some number that's not 0. Well, that's actually just equal to 0, right? 0 in the numerator is okay. Okay, and put a smiley face there as well, because we're done. 0 is my answer, I can move on. Scenario number 3 is going to be sort of the reciprocal of that, so a number that's not 0 over 0. Remember, 0 in the denominator is a no, so that means this is undefined. That's a D and E. I'm going to put a smiley face again because I just put D and E and I'm done with that question. So, scenario number 4. What scenario is left? Can you tell? So the scenario that's left is 0 over 0, okay? And this is what we call, I'd like for you to write, this is what we call indeterminate form. In other words, I can't quite determine yet what this is. Is it 1 because it's something over itself? Is it 0 because I have 0 in the numerator? Is it undefined because I have 0 in the denominator? It's not yet determined, right? So for these, do you remember we have to do more work, okay, to figure these out. Okay, so let's take a look at some of these scenarios, all right? So here's example 1. These are all determinant form. In other words, when I plug that value in for x, I'm going to get a nice number, okay? I don't have to do more. So I'm actually going to force a pause on your screen. Go ahead and write these down and try them on your own, okay? Once you've got them on your own, or you think you've got them, go ahead and press continue, and we'll take a look at the answers together. All right, answers are on the screen, so go ahead and get out that different colored pen or pencil. If you got it right, just put a little check with that different color. If you got it wrong, pause the screen and you can fix any errors you see there. I do want to point out here, make sure you remember order of operations. So that square is the last thing you do. First you find sine of pi over 2, and then you square that. So let's try example 2 here. So go ahead and write this in your notes. The limit as x approaches 2 of x minus 2 all over x squared plus x minus 6. So we always start by plugging this number in anywhere we see an x, right? But in this case, you see we're definitely going to get 0 in the numerator, and then in the denominator, I get 4 plus 2 minus 6, which is also 0. Okay, so in this case, I get 0 over 0, which means what? Means do more. Now, if this were a free response on the AP Calc exam, you would need to show, hey, I did get 0 over 0. So just putting that in parentheses somewhere is fine, but you've got to show them this is indeterminate form. I need to do some more work, okay? So let's do that more work. Now, the other thing you have to show is you can't just drop that limit, okay? If you put this, okay, and you start maybe factoring that denominator, you're going to lose points, okay, because these are not technically equivalent expressions. You've dropped that limit. So this is what we would call a linkage error, because you're saying two things are equal or are linked that are not, okay? So we've got to be really, really careful with our notation, especially when it comes to free response questions. All right, so I know I need to restart with that limit as x approaches 2. No, and I also know I need to do some more work, right? If you remember from pre-calc, the do more here is going to go ahead and be to factor. So there's nothing to factor in the numerator. Let's leave that as is. The great thing about factoring in calculus is you are typically given one of the factors there. So what is the remaining factor? It's going to be that x plus 3. So this is kind of my do more, right? I can see, okay, those divide out. So now let's rewrite what we have. We've got the limit as x approaches 2. Make sure you have that understood 1 in the numerator. Let's move this a bit. And then left in the denominator is x plus 3. Okay, now let's retry the limit. So now when you plug in 2 anywhere you see an x, I've got 1 over 2 plus 3, which is 5, and that's going to be our final answer. All right, I'm going to show you what the graph looks like of this function as well. All right, so here's the graph on Desmos, and we found the limit as x approaches 2, and if you look just from the graph, it looks like that function value exists, but if you get real close there, you can see, no it doesn't, okay? But that doesn't mean that the limit doesn't exist, right? So we found the limit to be 1/5. Let's see if we can verify that graphically. So as I'm approaching to the left, looks like we're approaching 0.2, and same as I'm approaching from the right, correct? And 0.2 is equivalent to 1/5, so it looks like we did good. All right, as practice, can you try the second one on this screen? So I'm going to force a pause on your page. Go ahead and write this and attempt it. Press continue when you're ready to see the answer. All right, so answers on the screen. Be sure you're taking out that different colored pen or pencil, either putting a check if you got it right or making any corrections above your original attempt in that different color if you need to. I'm going to ask for some feedback on this question and then we'll continue on. All right, here's example 3. I'm going to force a pause on your screen. Go ahead and write what I do, and then we'll write what's on my screen, and then we'll work this problem together. All right, so does this look familiar at all? Do you recognize that this is the signum function? That broken railroad tracks that we talked about in the very beginning. So this is the signum function, and which way is this shifted? So this is shifted to the left 3. Can you write that on your paper, please? Because remember, inside is horizontal and inside is also opposite. So we've shifted left 3. So we're taking those broken railroad tracks and shifting left 3, but not up or down, okay? So let's take a look here. Whenever you see these, the way to find the limits is, or the work I want you to show is to go ahead and graph it for me, okay? So we've got 1, 2, 3, left 3. Now the top y value is still positive 1, and the bottom y value is still negative 1, because remember, we've not shifted up or down, we've not stretched vertically or horizontally or anything, so we've just shifted that original graph to the left 3 units. So that's what it looks like here. All right, so now let's take this, and now we're just coming back to a regular limits graphically problem. So we want to find the limit as x approaches -3, the full limit here, right? So what do you think? What is this limit? So this limit is DNE, because notice what you're approaching from the left is -1, and what you're approaching from the right is +1. So since those are not equal, the full limit does not exist. The left limit exists, the right limit exists, but since they're different, you've got a jump discontinuity here, and the full limit does not exist. All right, here's example 4. I'm going to force a pause on your screen, copy what I have, and then we'll work it together. All right, so we want to find the limit of h of x as x approaches -1. This time we've got kind of a piecewise function, right? So let's think about each piece. The top piece, the restriction is for x's less than -1. So if I'm only looking at x's less than -1, which way am I approaching? Which limit would this sort of signify? So this would be the left limit. So I like to put right there left limit. All right, now the bottom, I've got x's greater than or equal to -1. Now, what does that equals part represent? The equals part represents the function value, which has no bearing on the limit, right? But the greater than -1, if I'm considering all x's greater than -1, then I'm coming from the right-hand side, right? So this would give me my right-hand limit. Okay, and to find the full limit, I need to consider both the left and the right, and I can see that they're split in this case. So let's go ahead and do that. Let's find the limit as x approaches -1 from the left of h of x. So in this case, would I use the top piece, the bottom piece, both, or neither? I would use the top piece, the left, right? So this is going to be the same as the limit as x approaches -1 from the left of that, which is just a constant 3. So I just get 3 for the left limit, okay? Now let's go ahead and find the limit as x approaches -1 from the right of h of x. So for this limit, would I want to use the top piece, the bottom piece, both, or neither? This time I want to use the bottom piece, right? So I'm going to take the limit as x approaches -1 from the right, and I'm going to grab that bottom piece, which is -3x. So now I'm going to plug in -1 anywhere I see an x, so that's going to be -3 times -1, which is 3. Okay, so does the full limit exist? It does, right? Because the left and the right-hand limit are the same, but I had to check both. So the full limit, we can say the limit as x approaches -1 of h of x is indeed 3. I'm going to show you this graph so you know what it looks like. So here's the graph. You can see as x approaches -1 from the left, my y's are there at 3, and as we approach 1 from the right, you can watch your y values there. They're inching up closer and closer to 3 as well. All right, so I'm going to leave you with example 5. It's a challenge problem. We will talk about it in class. See how you do with it. Go ahead and copy what I have on the screen and try it on your own. I do want to just kind of remind you, when you're looking at these restrictions, think about what each piece gives you. So does it give you the left-hand limit, the right-hand limit, the full limit, or the function value? Okay, so try this one on your own, see how you do. I will tell you that the limit does exist, so you should get to a value. All right, I will see you all in class.